So welcome everyone to this session. Today's talk is by Sinem Gichar-Yaman, entitled Specification and Verification of SLEEC Requirements for Resilient Autonomous Systems. And Sinem is a postdoctoral researcher in the Trustworthy, Adaptive and Autonomous Systems and Processes Research Group, as well as in the Resilience Node of the TAS Hub. And she obtained her PhD in Berlin, and the title of her PhD was Quantitative Verification for Evolving Software Systems. Her research focuses on software engineering, specifically on model-driven engineering and formal methods to develop solutions for reliable and resilient socio-technical systems. So we look forward to hearing from her today, and we welcome her. And over to you, Sinem.
Thank you very much, Bev, for the introduction. So good afternoon, everyone. Today I will give a talk on specification and verification of SLEEC requirements for resilient autonomous systems, or AI-enabled autonomous systems, in the scope of the Resilience Project. This project is a joint work with very valuable colleagues, including Radu, who is PI of this node, and Anna, who is co-PI. So I will start my talk with the motivation of this work and introduce SLEEC requirement specification afterwards. How do we encode the SLEEC requirements and SLEEC rules in a domain-specific language? Later on, I will then talk about the consistency validation, including conflict and redundancy detection. We then continue with the SLEEC requirements verification. I will also mention some extensions of this work with some external collaborators and also work in progress. I will conclude my talk with the future work and open questions and so on. So what is a resilient system? So I would like to start with the common definition of resilience. It must resist adversity and provide continuity of service, possibly under a degraded mode of operation, despite disturbances due to adverse events and conditions. And secondly, it must also recover rapidly from any harm that those disruptions might have caused. So looking at this definition, we can summarize that resilient systems are expected to continue and maintain their functionality in the presence of uncertainty and disruptions. So as an example to functional requirements can be a patient shall take their medicine between 8 and 8:30 a.m. This is like in a dressing, this is an assistive care, healthcare domain. So this is the kind of functional requirement, but what we say that we need actually socio-technical resilience in addition to functional and common non-functional requirements such as performance and reliability. What are these requirements and socio-technical requirements? We basically identify these requirements in 5 concerns or principles for the society's needs. So SLEEC basically stands for social, legal, ethical, empathetic, and cultural aspects of the norms and social norms. And we see that these requirements, a challenging type of new non-functional requirements. Why do we think so? Because these requirements are not for engineers to define, unlike non-functional requirements about resource use, utility, or reliability or response time. And they are deployment specific, and they rely on sophisticated system capabilities and subjective properties. For example, users' emotional state requires different fusion of the sensors or technologies. And as a motivation, it's also the case, it's supported by existing software engineering. It's fully supported by existing software engineering processes and tools. We know that there is huge consideration of the major ethical challenges of AI applications and robotic agents. But there is still open question So we don't know really how to operationalize these principles. So we need techniques and approaches to be able to like work and apply these principles in practice. In this problem, we propose a framework for the operationalization of the SLEEC requirements for AI agents. The first part of the framework basically considers the ethics, guidelines, legal norms, and takes these norms as an input, and these inputs actually is processed by the SLEEC experts for the rule elicitation of the SLEEC. So these experts also are aware of the AI agent capabilities as an input, and at the end of the rule elicitation process, experts can write some SLEEC rules. This process has been published in Minds and Machine paper by the colleagues. Once these rules are basically written by the experts, we can then formalize these rules in a mathematical language to analyze these rules if they are consistent each other. So which means that if they're conflicting each other or if there is any redundancy. So in this mechanism, we have the iterative process. So once we have the analysis results, we basically send this as a feedback to the experts, telling them there are conflicting rules and redundancies to decide to resolve these conflicts, to have a consistent rule set. Out of this process, we then include validated SLEEC rule sets. If we have the validated SLEEC rule sets and AI agent model, which is designed by the AI developers or system engineers or software engineers, we can then send these two input to the verification component to obtain verification results. In the verification terms, we here introduce the term of SLEEC awareness, which means that if the system considers normative principles in terms of SLEEC rules, so if they are SLEEC compliant, which is another way to say. However, from the whole framework and for the whole process, we can't really guarantee the success, because in the iterative process, we can provide feedback continuously that there are rules and conflicts and check again. At the end of this process, SLEEC experts might not agree on a SLEEC rule set and they can give up. Or autonomous systems cannot satisfy SLEEC requirements because of insufficient capabilities. And then we can't really provide a resolution action. What I would like to remind here, give a warning. So this process is actually, is not, so the framework itself is not really about specifying the right SLEEC requirements for specific use cases. Rather than that, it provides kind of framework and helps to encode these rules, helps the expert to understand the rules better, find a way, an automatic analysis of these rules and find a way to refine them, understand each other. At the end, on a consistent rule set, to be able to check if the systems are SLEEC compliant and SLEEC aware. It's also not possible to produce a set of rules, as Alan Turing said previously. So this is a general problem of the requirements engineering. We need to remember in this framework as well. So in this presentation, I will use some SLEEC rules for some case studies. The first study is, the case study is an assistive care robot in a home environment. I will show you a short video on this to understand the capabilities of the system, how it looks in the environment. This is a joint project between the University of York and PAL Robotics.
In the ALMI project, funded by the Assuring Autonomy International Program, the University of York and PAL Robotics, the focus is to develop adaptation methods for Tiago robot to be able to handle the uncertainty and disruptions encountered in a home environment. In this solution, the Tiago robot helps a user with mild motor and cognitive impairments by using both speech interaction and its object manipulation capabilities. This video shows an example of helping during the preparation of a meal and reacting to emergency situations. To achieve this, we created a simulation of the environment by using the gazebo simulator.
So the main purpose of the project is finding the safe path to the user in the environment with the highest probability. So it's about the mission planning. There are two scenarios: food preparation and emergency case. So I will speed up a bit because it gives more detail.
A graph depicting the environment is generated. Nodes represent the locations which the robot can access. The color of the edges represent the probability of successfully moving from one location to another. It takes into account the number of connections to other nodes and the probability of the path being obstructed by furniture. The framework uses this information to identify the path with the highest probability of success. We assume that the human moves following the shortest path from one location to another. The framework considers the human path for the planning of the robot's mission and adjusts the robot path to avoid collision. We use human recognition with NVIDIA Jetson NX, an external board to launch AI programs, providing more processing power.
Hello, Delia. Would you like to cook pasta?
Yes, please.
What is the food
Okay,
preparation scenario?
I will fetch the pasta then.
Interact with the user.
To start cooking, you need to boil some water.
Okay, thanks.
We use acapella onboard speech synthesis for generating speech with of York has integrated within the code to initialize, update, and get the advanced grasping package is a grasping pipeline for Tiago. The goal of this pipeline is to enable Tiago to grasp different objects in various environments in a modular and adaptable way. This is achieved by combining advanced robotic vision, behavior trees, and the motion planning framework movement. They allow the pipeline to be both modular and robust. These are the key elements of this grasping pipe tasks, such as object detection and table use case. The digital twin of the Tiago robot can be visualized in simultaneous to the execution of the task. Using OctoMap, Tiago maps the environment in order to avoid collision during planning. In this visualization, the detected objects are shown in green.
It's a lovely robot, but it's a bit slow, so I just speed up. Okay, so it guides.
What do I need to do?
For the food preparation.
Here is the pasta. Please put it in the boiling water and wait for 6 minutes.
Okay, thank you.
Pasta is ready. I will go to pick the tomato sauce.
So the important thing is that it really interacts with the user each time. So this is the first scenario. The second scenario is the emergency situation.
Tiago's mission is to roam the kitchen looking for any emergency situations. The OpenDR Toolkit is a set of deep learning software functions and packages to help develop and test robotic applications. Thanks to the OpenDR Toolkit, Tiago is able to detect a person that has fallen.
Tiago, help. Call someone, please.
We'll use Twilio to make an emergency call to the designated contact person. When a person is detected on the floor, Tiago will look for help.
So important thing is I want to show here that it has the capability to call for help or
Person.
some other
He will explain.
person.
The results from the ALMI project contribute to a better understanding of the user's need and the system requirements for developing a robot that supports.
Second one is the firefighter drone, which has some capabilities of fire detection, extinguishing, and alarming when in case of the fire.
It's going down.
Okay. So
In the ALMI.
So let's come back to the framework. So I will use this case studies for our requirements, and I will start how we encode the SLEEC rules into a domain-specific language, and how a SLEEC rule look like actually. So this is a SLEEC rule for the assistive care robot. A SLEEC rule has always a unique ID, and it has a base rule which has a trigger and response. And it's basically using divisible reasoning and using defeaters, which can be represented by defeaters. So in this case, when curtains open request and curtains open within 60 seconds for assistive care robot, we have unless user under duress, which handles the exceptions, then refuse request within 30 seconds. This is about the privacy issue if the user is under duress. We basically don't have this response to be open the curtains. And there is also an alternative construct for the rule with otherwise. So if the first rule, so if the base rule, base part of the rule is not achieved, so there is a timeout, then we can have the alternative within 30 seconds to repeat the request, for example. So as I said, the base rule has the triggers, which includes logical expression combining events and measures, so they look like this. So if we can have one event to trigger the response, but we can have the combinations of the measures and events. Events are atomic instantaneous actions, and measures are readable properties, which has like a type of Boolean, scale, and numeric. And then we have, there is an important thing to remember. These events and measures must correspond to capabilities of the autonomous agents. It means that we should consider some measures and events that are possible for an agent. For example, if the robot doesn't have the capability to detect the light, so it doesn't make sense to write a rule about this. And when we have the trigger, we have a response using within for a deadline. So the language, the SLEEC language, is a time language. So we need to specify some time for some specific events. So at the end, a SLEEC rule set looks like this. So it has two blocks. The first part is the definition block, where we describe the events and measures, like capabilities, and the second part is where we describe the rules. So coming back to the case studies we have seen in the videos, for the firefighter drone, we demonstrate here two rules. First rule says when battery critical, then alarm sounding. wait 40 seconds. This is quite a simple function rule, but when we come back to rule 2, when camera start and video record within maximum footage time, which is 4 in this case. Otherwise, if this is not achieved, we check the floors within 3 hours. Otherwise, if it's not possible as well, we check the areas within 2 hours, unless person nearby. So here again, there is a privacy issue as an exception. So if there is a person, we need to get the consent or we need to postpone the video recording. And this is a rule set for an assistive care robot, like again, a partial rule set. So as you remember, there is a food preparation scenario. Rule 1 actually considers some cultural concerns, and we here basically consider respect for religion and culture, because we say when lunch period started, and person's stress level is greater than light, we expect that the robot will advise user to consider eating in some minutes. If it's not achievable in the environment because of paid calculation or maybe because of other reasons, then this needs to be achieved within 5 minutes, for example. But unless praying time, so we have an exception here, which considers the religious situations. So if it's a praying time, the robot shouldn't disturb the user. But we have another defeater, which says unless not lost meal time is greater than maximum time. So if the user hasn't eaten like for a long time, then the robot should take an action. The religious respect for religion is important, but this is a preventing harm because the user hasn't eaten meal for a long time. In the second rule, for the user fallen case, we know that when user fallen, then support call within 2 minutes, but unless not person assent, the user might not agree to be called by emergency service. He or she wants to call somebody else, or maybe he or she thinks that it's not serious thing. So these events and measures are important to show off this video, to remember this video. The robot has these capabilities to identify these measures. Okay, when we have the rule formalization, rules encoded in a language, we then describe them in a formal semantics in tock-CSP and then validate them for consistency. For this purpose, we developed a tool which is in the Eclipse environment. So we have a DSL editor that we can write SLEEC-rule. So it has like kind of highlighting, type checking, helps the user to write correct syntactical rules. And then we translate it into a tock-CSP language to send it to external model checker, FDR checker, to identify these conflicts and redundancy. Yeah, the tool is publicly available on GitHub, and on the website you can find more information. I don't want to go into the details of the formal semantics. There is quite a bit of work behind this translation, but just give an idea of how it works. So basically, tock-CSP is based on process algebraic semantics. It's formal programmatic, and the processes define patterns of interaction and atomic and instantaneous events are channels, basically. And there are non-determinism, deadlock, live lock, and termination. Tock-CSP is a special CSP event called tock, which is 1 second in this case, so it's 1 time unit. And in our approach, SLEEC events and measures become CSP events that are channels that connects the processes. And measures are always available. We read them with deadline 0. And rules are defined by the processes. Okay, this is a very simple example. So in the rule rule 2a, we have when user fallen, then support call. We don't have a deadline, so it can happen anytime. User fallen, so in the second blue box, you see the translation into tock-CSP. We have the events happening, user fallen, support call, and the recursion. Or as an external choice of the process, we have the support call, again, the recursion. To give an idea of how these processes look like, we can look at the traces, characterize the behavior a lot for this process. So it can be an empty set, or it can be support call, and support call, because this is a recursion. Or it can be the case tock. Tock means that the time passes, then support call is fired, and then time passes again. So the other possibility that the event user fallen happens, and then support call is expected to happen for this trace, and the time passes, and then user fallen, support call, and then we can have multiple examples of this. Yeah, for the defeaters, I don't want you to get lost in this semantics, but just give the idea of the defeaters in the language. When we have a rule, when user fallen and support call within 1 minute, unless not assigned to support call, then open curtains, unless emergency. We basically handle these defeaters bottom up. So for every response, for example, response support call, we have the first monitoring one is a response. It says in 60 seconds, because it's 1 minute, we translate into seconds. Support call, and then monitoring 2 as a response open curtain with skip. And monitoring 3 doesn't have a response, so it's just skip. And how we handle it is just bottom up with the else structure by reading the measures like SON to support calls or emergency. If they are true, then these actions, these responses will be fired. Yeah, so there are some examples of traces. We can have the event user fallen, and emergency is a Boolean type, so it can be false. Assigned to support call is a Boolean type, it can be true. And this trace can happen with multiple talks until 59, but no more, because we have the deadline with one minute. So this is basically an example of a trace. When we have these rules, we check them in the FDR model checker if they are conflicting. So let me explain how this works with examples. So there are like 2 rules for a firefighter drone. The first rule says when battery critical and temperature is less than 25, then go home within 1 minute. So this rule implies that there is no fire risk, judging by the low temperature. And the battery reaches a critical, so it should go home base to fill the battery. In the second rule, when fire alarm sounding, there is an emergency danger, indicates the likely presence of a nearby fire, then it shouldn't go home within 5 minutes. Do you spot any conflict or see any conflict here? We can see that there is something is not true for some rules, because one is talking about the emergency case, the other one is saying, oh, go home and then get the battery. And our tool basically gives a deadlock with a counterexample, because the first rule indicates a non-emergency case, so it can go home within 1 minute. But the second rule says that in 5 minutes, it shouldn't go home. Basically, both rules restrict go home event. So we have a conflict in this case. So we can ask the experts to identify a solution for the resolution of the rule set. There is another example for the dressing case. rule 1 says when curtains open requested, then curtains open within 6 seconds. Unless user underdressed, then refuse request within 3 seconds. Unless user distress is greater than medium, then we should open the curtains within 60 seconds. So there is a privacy issue, but then there is another defeater says that, oh, the user looks stressful. We should open the curtains. Maybe the user doesn't care about being underdressed or undressed. The second rule says when curtains open requested and user underdressed, then not curtains open within 60 seconds. So we get a conflict here because we have a deadlock again. And here the question is, how do we understand the conflict? And the answer is the first one, in the first rule, when the user asks for the curtains to be opened, is who is underdressed, so it's true, and has a distress level above medium, rule 1 demands that the robot should open the curtains within 6 seconds. However, in the same circumstances, rule 2 disallows the opening of the curtains for 60 seconds. So do you understand this problem here? Okay, if we understand the problem, how can we solve this? There are possible ways maybe to have an agreement on this rule. So the stakeholders could decide to remove rule 2 because it's really doesn't make sense with rule 1. So it really forces the opening of the curtains for the same circumstance. Or the stakeholders say remove the second defeater from the first rule, or they might suggest to relax the deadlines and see what happens to refine the rule set. This is another example. I'm giving different examples because they are different situations. We can call it a subtle conflict between these two rules. It looks like a same rule, so it's talking about the same thing when curtains open request and curtains opened. The second one has deadlines, the first one doesn't have, and there is also other difference. The second one has a measure which is called user underdressed, and the other one user undressed. These rules were like from the case study we use that were written by different experts. So actually they wanted to say same thing with different definitions, and our tool detects this as a conflict. Because user undress is true, but user underdress is false for a trace in the counter example for the same response to happen. So how do we solve this? We send this as a feedback to the user and to stakeholders, say that, oh, okay, they realized, oh, they mean the same thing. So after refinement, conflict resolved. This is another conflicting example, but this is a different type because you can see rule C and D, they look very similar with the same defeaters, but the order of the defeaters are different. So here we don't identify a deadlock, time deadlock. However, when the battery level is critical, there is a person nearby and the temperature is above 35 degrees. Rule C demands that the drone sounds the alarm and prevents it from going home. Rule D demands the drone to go home and prevents it from sounding the alarm. So we basically identify this as a conflict as well. So far I showed examples of conflicting rules. And now we have some examples for redundancy. So you can see this is an example for firefighter drone again. Rule A says when camera start and person nearby, then sound alarm. Rule B is saying the same thing with a deadline. So basically, this is actually a trivial example for a redundancy, because we can see that rule A is weaker as it doesn't have a deadline and it can be removed from the requirement set. So this is basically identify using refinement checker in the FTR tool. Of course, the first example was a trivial for redundancy, but we can have really a large set of rules for large systems, robotic systems and AI systems, and it's not easy to detect these redundancies by human. In this situation, this is a bit more complex redundancy. The first one is saying the same thing with multiple defeaters. So one user fallen, then support call within 2 minutes, unless not assigned to support calls, unless emergency, and the second one without defeaters. So the tool identifies rule 12 is redundant with respect to rule 13. Okay, when we have this conflict and redundancy checking, and after refinement of the rule set, and if we have an AI agent model, we can then send this to input to verification to see if the system is complying with the SLEEC requirements. For this, we need 2 inputs. The first one is the robot chart model of the system. In this case, this is a firefighter drone. And the second one is the SLEEC specification for a firefighter drone. Why we pick the robot chart modeling? So it's a graphical model. So it enables us to use the editor. Otherwise, we need a CSP language to encode to see if they are complying with the SLEEC rules. When we have the robot chart model, we can translate. So there is an automatic translation from robot chart model into CSP language. It's same for SLEEC-rule, so they can speak in the same language, and we can use the refinement checking to understand if the rules are compliant. If the system is compliant with the rules. So robot chart model is actually adopting many elements from the UML state charts. It allows to parallel execution of state charts, so there are like nested structures. There is this synchronous or asynchronous communication. It's platform independent, and the capabilities are defined by events and operations. But in addition to UML state chart, it has time, which has a similar idea of like time automata. In this case, with talks. So it has basically states and transitions and junctions on the transitions, which are like constraints. So on the second input, the rule set, we see that, okay, in the iterative process, rule 1 is redundant, and this needs to be removed. So we don't need to check if it's complying with the system. So what we can do is that we can have the refined rule set and the robot chart model, and see if it satisfies the rules. The first rule satisfies the model satisfies the first rule. Sorry, rule 2: when camera start and person nearby, then sound alarm within 2 seconds. The time also works. But the second rule, so rule 3, when sound alarm then not go home within 5 minutes, is not satisfied. We get a counter example. As you can see, the system allows to go home in this time period. So we get this counter example, which violates that behavior. So as a summary of this framework, basically we evaluated our SLEEC language expressivity and usability with multiple experts from different domains. So we used, in the experiments, we had 6 experts, and we allowed them to imagine naive capabilities. They had background in psychology, ethics, law, oral psychology, goal modeling, engineering, and so on. And then we also evaluated the framework of the correctness, scalability, and usability. We identified for like 21 rule sets, 3 conflicts and 6 redundancies. And out of these 21 rules, 9 were using naive capabilities imagined by the experts. So in the verification, we had 16 valid rules after the iteration of the process. So 21 rules, reduced to 16 rules after the resolution of the conflicts and redundancies. And then 5 of them were relevant to the system capabilities. So we have the notion of the relevance here, because if the rules, the capabilities of the rules are not subsets of the system capabilities, it doesn't make sense to check if it satisfies, because it will, the events will not be triggered at all. So it will not be able to verify the system. So basically, from the 16 rules, we had 5 using on the system capabilities, and out of these 5, 4 rules were satisfied and 1 rules were violated. So we released the models, case studies, and the whole code in the GitHub again. Yeah, so far I explained the whole framework we developed in the scope of this project, but there are also other extensions and tool improvements with some colleagues from University of Toronto. What we did in the ASC paper, we improved the tool with feedback mechanisms. So you remember we provided some counterexamples to the experts from the FTR model checker, which might be difficult to understand by the experts. So in this tool, we have, for example, we say there is a redundant rule, rule 5, and it highlights the parts which cause this redundancy, or which like is relevant to the redundancy. And then there is another output, say, provides a hint and diagnosis to the user. For example, it gives like an output saying, oh, within 1 minute is actually equivalent to within 60 seconds. Or room temperature is less than 16 implies room temperature is 17. So this is like easier for the expert to understand the rule and to make a decision on the resolution action. There is also another improvement of the SLEEC requirements analysis, which is N-check approach, has been conditionally accepted in ICSE this year. We got quite positive feedback. The first contribution of the work is that there is an extension of the consistency analysis in addition to conflicts and redundancy. So we have different type of conflicts: vacuous conflicts, situational conflicts, redundancy, insufficiency, restrictiveness. Like these definitions come from the requirements engineering processes. And then well-formedness, so we call this well-formedness properties, and they are mapped to SAT problem. And we use a specific logic to translate SLEEC rules into this logic. And we compute a diagnosis via causal satisfiability proof analysis out of this. The second contribution of this work is actually we really conducted a user study with 9 case studies from different domains. These domains are really various. So the ALME project from social care, you've seen the video. ASPAN is a project on the environment and protecting tree from some disease. We have DAISY, again, from healthcare, used in a robot used in the triage scenario. We have some examples of transport, healthcare, education, social care, and manufacturing. We really conducted kind of more than 10-12 hours experimental user study with experts from multiple domains. So we had lawyers, roboticists, ethicists, psychologists, sociologists, and engineers. The benefit of this approach to use SAT solving was also outperforming the process algebra approach in the sense of the time efficiency. So you could analyze these type of consistency check for these large set of case studies in seconds. And the results in terms of true positive and false positives were quite okay out of this analysis. Yeah, so there is also work in progress. This is a very interesting extension of the work for the mission planning. So you have seen the ALMI video that we like to. So this basically robot has a mission planning with task scheduling. So it has these 3 components: task scheduler, human predictive modeling, path planner. But on the top of this architecture, we would like to have a SLEEC-aware architecture that considers SLEEC rules with a SLEEC reasoner. So our goal is really to synthesize from SLEEC requirements to task scheduling for SLEEC compliant mission planning, or for SLEEC compliant assistive care robots in this scenario. There is also future work I would like to mention. So this is a video showing, this is an RE robot in our lab at Institute for Safe Autonomy. So I will show the robot how it looks like in the dark. Thanks to my colleague Carla Memory. So this is actually functionally perfectly working, because basically the robot needs to give some warning, some lights when there is a warning. So I don't know exactly the functionality of the robot, but when the lights are off, so there is actually a disruption for a SLEEC concern. So everything looks fine when the lights are on, and we can say the SLEEC requirements are satisfied because there is no problem with annoying the user. But in the case of when we change the measures or environment conditions, there is a disruption for SLEEC requirements. Actually, there is no problem with the functional requirement, but it looks a bit scary for maybe elderly people from the SLEEC concern perspective. Okay, so I described, as a summary, I described and introduced an end-to-end tool-supported framework for the elicitation, specification, consistency, validation, and verification of SLEEC requirements for autonomous agents and AI-enabled agents. Of course, there is a lot to do next. We need more tools, more applications, and SLEEC-aware plan synthesis, repair, and runtime adaptation when we have some disruptions at runtime. You can find more information about the SLEEC framework on the SLEEC webpage and in the GitHub repository for the tool models and so on, and in the publications. Thank you very much. So I'm happy to answer your questions and happy to get also feedbacks and collaborate if you have some ideas for open questions. Thank you.
Thank you, Sinem. Thank you very much. It was exceptionally interesting. If there are any questions, you can just put your hand up and we can ask them now, or if you'd like to put them in the chat. Or if not, we can just wrap it up. Any questions? I can't sort of see any hands going up. We have a question. Would you like to go ahead and ask the question, please?
Yeah, sure. Thank you very much, Sinem, for the good presentation. So my question is more about the use of the SLEEC requirement. Who do you think will be the receiving end of such a SLEEC requirement, as they, in your tools, describe that they were provided by domain experts, but the person who interacts with the users is actually be responsible for whether those rules applies to them or not. So how do you see the actual use of such thing?
At the moment, we see that these rules need to be written by really experts that have domain knowledge and have some certificate or have knowledge on the guidelines, ethical guidelines or regulations and so on. So we haven't investigated in the writing rules by any user as an interaction. So in the current stage, because SLEEC requirements are they need to be, so we also don't expect the engineers write them. So if there is a cultural rule, a sociologist should write the rules. We envision in this way. So it can be personalized. So there are some works in this domain, like how to profile, like having the human values in the rules. So they can be personalized by using profiling, for example. But this can be interesting. So at this stage, the input is coming from the experts that have domain knowledge.
Thank you for that. We actually have a question in the chat. So I don't know if you'd like to go ahead and ask your question, or I can read it out.
Yes, of course. Thank you, Sinem. It was very interesting. I was wondering if you're expecting to have some explainability framework for the actions that the autonomous system is taking at runtime, or are the SLEEC rules and how everything is enough to understand the train of action?
Actually, yeah, explainability is a very important thing. Thank you. We can have a component which handles the explainability because the feedback mechanism from the analysis and from the robot, they might not be clear enough to the experts and stakeholders, to the engineers. So I think this is something what we are doing, like it's an extension because this is required for explainability, I believe, if this is your question.
Yes, thank you.
Okay, are there any other questions? I don't see any others. So I think if that's it, we are now 5 minutes to 6, well, 5 minutes to 4. So I think thank you very much for attending. Oh, we do have another question. Would you
Okay,
like to?
no one is asking.
Yeah, you have a follow-on question? Okay, feel free to.
Yes. I was wondering also if you're thinking in some kind of self-adaptation where the rules can be adapted if some are if some needs to be updated or circumstances changes, maybe context aware.
Yeah, that's a good question. We are also considering this. So the context might change and SLEEC rules might, so it might be the case some SLEEC rules are not relevant at all, and maybe they are not satisfied and they need to be updated. So we really consider this in the self-adaptation case.
Okay, thank you.
We are happy to collaborate on these problems.
Perfect.
Okay, well, thank you everyone, and thank you for your time and your effort. And wait, there's a clapping. But if there aren't any more questions, then thank you, and I think we can end it here.
Thank you very much.